My name is Piotr, and I would like to say something about matrices, tensors, and how to name them and how to visualize them. My background is quantum physics and also AI, or deep learning. So hi, or привет. So the first question is, what is the matrix? There's one answer, but for the sake of this talk, I would prefer something much simpler. Just a table with numbers. And when it comes to this talk, well, I would like to start with matrices in pure Python, with NumPy and Pandas, how to visualize them, and how does it work in deep learning and quantum physics. And afterwards, well, we'll see. Though, to be honest, I'm kind of skeptical because, when it's online, no one wants to turn on their voice just to laugh or just applause. But we'll see. When it comes to Python, well, can we use Python to type matrices? We can. The name is important. Of course, it's because it's a list of lists, not the League of Legends or anything. And we can do simple operations. So we can check every entry. We can take a row. We can take a column. Though, maybe it's not the most convenient. And in principle, we can do matrices in Python, pure Python. But just because we can do something, it doesn't mean, well, we should. And I think it's a general good piece of advice for life. Why? Well, it's slow. At the same time, it's not that it's slow, but super convenient. Well, it isn't. Also, we don't know if it's only numbers or numbers, strings, and anything. Or we don't even know if it's a square or rectangular or anything. So it's not that useful. Next, the NumPy. So basically, when you think about matrices and arrays in Python, usually we think about NumPy. It's the backbone for any numerics in Python, basically. We converted our stuff into an array. It works. Moreover, when it comes to simpler operations, either they are simple, or they are simpler, or they're more expressive. For example, it's not that hard to subtract rows or columns. And you can see what's going on. For example, you can see if it's float or any other type. And what's next? Well, the good part is it's fast. Under the hood, well, it's very, very optimized code. It's as fast as in C, basically. And there are quite a few features, especially when you use SciPy, which is a whole package for scientific computing. So what's missing? Well, it depends on the problem, but in many cases, we do care about what are the columns. So if it's like salary, is it, I don't know, number of employees, is it temperature or anything? So let's use Pandas. I think everyone knows Pandas. Though I started using numerics in Python before Pandas was cool, at least before Pandas was mature enough for production. So we can add columns, indices, and I think one nice thing about using columns and index names is that we can access them. So we can look at one entry, a row. We can make, I don't know, say mean or sum or any other operation and see what happens. We can access any element the same way. We can perform other operations. So there's one column, but also we can say what's sweet minus bitter. And it works. It's much easier, and it's important, especially when we load data from, say, a CSV file, and maybe the order is different each time, and we don't want to get into some nasty mistakes just because the order of columns is different. And is it all? Well, Maybe, maybe not. It's a very, very poor pastiche, a very bad taste, but I have to say that here. But I know every frame and row and column has a type, has an API, has a name. It's kind of from colors of the wind. So, well, let's add colors. We can use Seaborn. This is very nice. I like very much this cool one. Scale. We have a table with columns and also names. And a scale. Very often we want to go slightly further and say add numbers. So we have the best of both worlds. Sometimes we also can play with other stuff. For example, we can play with clustering. And then it's not only that we have a table, but also we can arrange rows and columns in a way that the similar ones are near to each other. And I think it's important, especially because very, very often data is not ordered and we can arrange it anyway. So why not arrange it in a way that makes sense? And is the most sense. I can try it, like if it's possible to enforce other format. For example, one. Yep. So, well, this is some issue with aligning, but we have also numbers. So next, well, you can make it interactive. This is a cluster grammar, one thing which is for clustering, but it's interactive. You can play it with it in Python. You see how it works. It's initialized. And it's there. We can play with it. So it's not only it's a heat map, but also we can mouse over, we can arrange it, we can sort it. For just a few entries is not that important. If there are more entries, it's super important and super useful. So we can not only have one order, but pick order depending on our goal. For example, compare everything to Spicy or compare everything to, say, Alex preferences. Okay, so let's say, okay, we know how to do computing which is performant. We know how to describe columns and rows. We know how to make heat maps. So is it all? Well, for matrices maybe, but there are other things in the universe. So I think the scalars, like temperature, vectors. Why tensors? Why 2 dimensions? Like why 3 dimensions? 4, 5, 10. Well, from quite a few things we need to do. For example, for advanced physics. But is it all? Is it only advanced physics? Well, also simpler things. For example, images, width, height, and channels, so RGB, or maybe the transparency. And in deep learning, very often we don't process single images. We put them in batches, so produce a few images at the same time. And there's like sample, height, width, channel. Or maybe it isn't. Maybe it's, I don't know, sample channel, height, width, or sample channel, width, height. But I don't know, okay, it's not a problem. Let's see what's the convention, let's memorize it, and with some practice, we'll know each time what's the order. So, let's see. OpenCV. There are 2 depending if it's grayscale or not. Fluid the same, non-fluid same, nice. Piano different. TensorFlow also different. PyTorch the same as Tiano. Well, there's some room for confusion. And for me, like when the first time I heard Piano tensor dimension order, it sounds like there's some secret convent from a conspiracy theory. And even worse, sometimes within the same framework, we can use different dimension orderings. It's not because of being clumsy. It's not because developers are lazy. It's because when it comes to performance, sometimes one order is better than the other for one operation, and for the other, the different order is more performant. So how to deal with that? You can remember, but I will see how to solve the problems. Okay, so let's go to PyTorch. I love it. It's a beautiful thing. I think it's super nice to write. It has super nice error messages, which is important. And just I love it. So let's define a tensor. See this is there. It's kind of the experience is kind of similar than when it comes to when it's NumPy. So it's X, data type. You can look at size, which is shape, 1, 3, 3. But okay, which three is which? You can look at averages of stuff. And okay, dimension 1. But what's that exactly? So we can go a step further and use so-called named tensors. They're introduced in PyTorch 1.4. They are still experimental. So, well, use them with care. Still, I like to use them. So we can name a tensor, and it's the same thing, just with one thing. What's the name of each dimension? So like sample, channel, height, width, or the other way. And we can use a few very, very interesting things. So for example, we can make average when it comes to channel. And we see the remaining vectors, and our average with respect to other thing. For example, with respect to age. Or like maybe even 2. There are 2 or more. I don't know. Everything by leaving everything but the number. Here and here. So it's very, very versatile, but what's the most important, we know what we are doing. And we know what they are the results. We can also change the order, the same, I don't know, change. I know, see with the last one, we see what's going on. So it's very, very flexible. And we know what it is out. Or it's like what's actually very important, very often we need to flatten some dimensions. So basically turn a tensor with 4 dimensions into a matrix. We can do so. Otherwise, it's kind of clumsy and so error prone. And it prevents from the simplest errors. So here we have, say, 2 matrices, and we want to add them. And rightfully, we get an error. How to fix that? Of course, we can change H, W, and now we get our result. I think it's very important because it's better to get an error than to get an answer which is incorrect. And then, especially in deep learning, when it's like there's many operations, so it's very, very hard to debug because there's no error, still we get the wrong result. Well, so we can use dimension names in tensors. Why not using it in neural networks, right? It's the obvious application. So let's PyTorch, let's create input vector and see if you can use it with the dense layer. It's the simplest layer in deep learning. And we get something. But we see it's not longer there. This N is nice. But, well, so let's test. What happens if, say, we change things here? Well, yes. Oh, well. So it means that it does nothing, just interprets one name, and otherwise it doesn't control if these things make sense. And for deep learning, it does not in this case. What's even worse? I'm trying to use conditional layer, so the simplest layer for any network for image processing, you get an error. You cannot do that at all. It's not because the order is wrong. We cannot use this operation. Well, let's see why. So basically, error message, which again I adore PyTorch error messages. We see what's going on. Says that we need to drop it, otherwise it won't work. So, well, the first response is, yeah, it's kind of suck. But the second one is like, well, it's a solution. So we know what to do, so to solve the problem. So what do you do? Well, we create a package, very, very small one, so that all layers have their dimensions. because in all documentation, there is a specified order of dimensions for each operation. It's not yet on PyPy, but you can install it directly from Git. It's the first version of actually 0.1. We will use that. So for example, you can install it, use it and create operations. See that instead of NN for layers, we get from neural networks, it's like NM from named layers. And for some operations, we use NM. The same operation technically, just with dimensions. So when you put things, it works. Of course, it's random data, so each time is different. But let's see what happens if you put different data. So it's this thing, there's an error. Not because it's a mistake, not because it's not implemented, just because there's different order of dimensions. So, but it's not that bad. So it's not like that we have to specify dimensions beforehand. First, we need to, we can create a tensor without all dimensions, for example, NC num, and still we get a result. Even like actually, I think that we can do none here, it's fine. So it does not require input to have named dimensions, but if it does, it checks that. It's one nice thing. And we can use it later. So but the question is like going one step further, quantum mechanics. So it's, if you say that, okay, AI is difficult, what about quantum mechanics? Well, I don't want to explain quantum mechanics in a few minutes because it's hard, even impossible, but I want to show a few nice pictures. So first thing, when it comes to quantum mechanics, it uses complex numbers. That's slightly strange, but not that because they're even in basic Python. The next thing is that there are as many dimensions as particles. So if there are 10 particles, there are 10 dimensions. And for operations, there are twice as much because there are input and output dimensions. So we have Qtip, which is a package for quantum information, quantum computing in Python. It's a very nice one, based on NumPy, by the way. And just a few and there's a visualization, and just I want to show pictures. I don't want to explain. This is the simplest entangled, say, very quantum state. The picture of it, another one, picture for more states, like the 4 particles, or 3, yes, 4 particles. And there's some visualizations that basically allow us to use any number of dimensions. Maybe like 10 pixels are very, very small. What we can do it also? Well, we can use a newer package, which I released, we released this year, which is interactive for quantum computing, and quantum information, and quantum physics. It is JavaScript. I tried to put it inside Jupyter, but it was hard, kind of difficult. So I used something different. I used JSPiddle. It's a tool that you can write some script and you can see the result. It's not operation. So like it turns 0 into 1, and vice versa, and we describe it as a matrix. Okay, code is here, it's not that bad. HTML, it's even simpler. You can look what's going on. In quantum mechanics, there are other stuff. For example, we can have so-called square root of node. So basically it turns 0 to 1 and 0, and 1 also to 1 and 0, but in a different way. So-called phase, like it's 0 minus 1. You can look here, but it's not. It's just one particle. For 2 particles, it's also compressed to 2 dimensions. Is that you can have C0 operation, which is turns the other bit only if the first one is 1. So see, with 0 is the same. With the first one, see here, is 1. Then we flip the other. Other operation which is also useful is Toffoli gate, which is some kind of quantum AND operation. Things get more complicated. We have 3 particles, and there are also 3 outputs. And we can see that it's always the same unless 2 bits or qubits are 1, so that the other one, the last one, gets flipped. We can play with that. For example, you can play with so-called bases. It's like just, in this case, it's more like data art, but I like it. I like looking at it. So with this data art stuff, I would like to finish this illustration. Oh, there's actually one more. It's like it's physics. It's like beam splitter. When you have light shining on beam splitter, it gets reflected, part of it passes, and we get what happens with both direction and so-called polarization, so what the property of light. And we can play with bases, so a few ways to describe how the light behaves. Again, there are 2 input dimensions, 2 output dimensions. Still we can present that, even complex numbers, as a table. And well, that's it. So I hope like I inspired you how to use Python for matrices and gave some insight in deep learning and quantum physics, even if at the level of pictures. If you want to learn more, there are quite a few links, and also like there's some advertisement of Libelus Plot, which is a package for charts for deep learning. And well, there are the slides. So just if you want to, there's also create interactive presentation. This is a nice one. Nice tool to do so. Thank you.